Okay, so welcome to Math 331 little question, lecture 3. And what I wanted to do today was to continue the conversation on recurrence relations and the tiling problem. And so this is an opportunity to get a publication. So I am, as I mentioned, problem editor in many places, managing editor in many places. I think this would be a fun problem. It's also an interesting way to start getting into some research. Always take a question and see, can you push it further? If people are looking for other opportunities, I mentioned the math outreach article we could write based on trying to get some intuition for the product world. And again, the world is the way it is. That's way beyond my pay grade. But if you were to create things, there would be a tendency to say the derivative of a product should be the product of the derivatives. The derivative of a quotient should be the quotient of the derivatives. It's not that way. How can you sniff out what the true formula is? And we talked about looking at a couple of simple functions, playing with them and building intuition. That's one of the skills I want you to get out of this class. How do you build some intuitions? And we'll talk a little bit more about that when we look at the Fibonacci numbers. So let's just normalize things. There's lots of different ways you can define the Fibonacci numbers. For today, I'll start with F0 is 0, F1 is 1, Fn plus 1 is Fn plus Fn minus 1. And we mentioned Benet's formula last time, yes? Okay, and what's nice is I can always just go back and just check a few slides ago to see did we really mention it or not. Let's get some feel for the size of the Fibonacci numbers. We know, Fn plus 1 is going to be less than or equal to twice Fn. Because the Fibonacci numbers are clearly non-decreasing. So if I replace Fn minus 1 with Fn, as Fn minus 1 is less than or equal to Fn. So what this tells us is the Fibonacci numbers are growing slower than 2 to the n. So we have Fn plus 1 would be less than or equal to 2 times 2 Fn minus 1, which would be less than or equal to 2 times 2 times 2 times Fn minus 2, ... And when we're looking at something like this, the question is always, how do I finish this in the end? How many 2's do I have if I want to go all the way down to either F0 or F1? Well, I notice that when I have 2 Fn, the power of 2 and the index n adds up to n plus 1. When I look at the next one, I have 2 squared and Fn minus 1. It adds up again to n plus 1. So I will get that Fn plus 1 is going to be less than or equal to 2 to the n plus 1. So we know the Fibonacci numbers are growing no faster than geometrically, no faster than 2 to a power. Everybody comfortable with this? I'm a little confused. Okay, so do you agree that the Fibonacci numbers are not decreasing, that each Fibonacci number is less than or equal to the previous? So in the recurrence Fn plus Fn minus 1, if I replace Fn minus 1 with Fn, I've only made things potentially larger. I can't make things smaller. So I know Fn plus 1 is less than or equal to twice Fn. Because Fn minus 1 is less than or equal to Fn, so Fn plus Fn minus 1 is at most Fn plus Fn. So each Fibonacci number is at most twice the previous. And so if Fn plus 1 is twice Fn, and Fn is twice Fn minus 1, then Fn plus 1 would be at most 2 times Fn minus 1. And I can keep going like this, and I can see that the Fibonacci numbers are not growing faster than 2 to the n. We can do it on the other side. So this would be the upper bound. Can somebody give me a lower bound for Fn plus 1? So what would be a lower bound for Fn plus 1? 2 Fn minus 1. So what this is telling us is every time we increase the index by 2, we at least increase by a factor of 2. So with a little bit of algebra, which I don't want to do, we basically get that Fn is greater than or equal to the square root of 2 to the n. I'm going to say basically because maybe there's a little bit of an issue when n is small. N is 1, for instance. I'm not saying f1 is greater than square root of 2. But eventually this is going to be true. And the reason is every time we increase n by 2, we get a factor of 2. So root 2 times root 2 is 2. So we have essentially root 2 to the n is less than equal to fn is less than equal to 2 to the n. Put this in quotes. Maybe fn is like r to the n for some r. And again, my goal is to try to give you a feel for how you would get to answers. Let me try to look at some extreme cases. Let me try to get some upper and lower bounds. Let me get a sense for how things are behaving. So it's growing at least as fast as root 2 to the n. It's not growing faster than 2 to the n. Maybe it's growing at some intermediate rate. And so what we can now do is we can guess. Let's try fn is r to the n. Then we would get, fn plus 1 equals fn plus fn minus 1 becomes r to the n plus 1 equals r to the n plus r to the n minus 1. Divide by r to the n minus 1. Why can I divide by r to the n minus 1? It's a common factor. Am I allowed to divide by any common factor? As long as it's not 0. Because if I equals 0, then I'm just getting, fn equals 0 to the n. That is a solution to the Fibonacci recurrence. If I want to solve fn plus 1 equals fn plus fn minus 1, if I take every term to be 0, does it satisfy the recurrence? Yeah, it just doesn't satisfy the initial condition. So that would lead to r squared equals r plus 1, or r squared minus r minus 1 equals 0. This is called the characteristic polynomial for the recurrence. How would we solve this? Quadratic formula. What else could we do? We could try to factor it. Unfortunately, this does not have nice, integer roots. It does not have nice rational roots. So we need to, use the quadratic formula. That's not so bad, right? And so if we want to solve r squared minus r minus 1, this is just your ax squared plus bx plus c. A equals 1, b equals -1, c equals -1. So we get the roots. R equals 1 plus or minus the square root of 5 over 2. So if we call these R1 and R2, so R1 to the n and R2 to the n solve the recurrence. So 2 does, A1 R1 to the n plus A2 R2 to the n for any A1 and A2. So I'll leave that as an algebra exercise for you. Because R1 and R2 satisfy R1 to the n plus 1 equals R1 to the n plus R1 to the n minus 1, if I multiplied everything by 5, it would still satisfy that. Because if I look at the recurrence, if I have a sequence that satisfies the recurrence relation, if I multiply every term by 5, it's still going to satisfy the recurrence relation, right? When we look at this, if I multiply every term by 5, is that still a solution? Yeah. If I multiply every term by 3, is it still a solution? Yeah. If you want, think of the Fibonacci numbers as lengths, and they satisfy this recurrence. And I decide I'm no longer going to be measuring things in yards. I'm going to measure things in feet. I, of course, should never measure in either of these units, but let's say we're doing that. To convert from yards to feet, I just multiply by 3. And I would have a new sequence of numbers. It would still satisfy this recurrence. So if I have a sequence that satisfies a recurrence like this, I can multiply every term by 3 or 5 or by any constant, and it will still work. If I have two different sequences that satisfy this recurrence, if I add them, it satisfies this recurrence. This is one of the reasons why linear algebra is a nice prereq for a class like this. You've hopefully seen something like this where when can you combine different solutions? Well, you've hopefully seen something like this with subspaces. If I have two vectors that are in a subspace, the linear combination is in the subspace. That's what we're doing down here. And so I'll leave this as an exercise for you to go through and do the algebra and show that this works. And then with our initial conditions, we get our conditions, f0 equals 0, f1 equals 1, leads to fn is 1 over root 5, 1 to the n, minus 1 over root 5, 2 to the n. And this is the one with the plus root. This is the one with the minus root. So this is one way to prove Benet's formula. Okay? It's one of my favorite formulas in all of mathematics. It gives us a closed form solution. And so what I want to do is I want to ask you a couple of problems for you to think about. And these are related to possible problems that we can propose for the journal. So new problems. So let's consider an plus 1 equals alpha an plus beta an minus 1, with 0 less than equal to alpha beta, and maybe in one case, alpha plus beta equals 1. In another case, alpha squared plus beta squared equals 1. And maybe in another case, maybe alpha to the 1/2 plus beta to the 1/2 equals 1. For each of these, you can play the game we played a moment ago. For each, find alpha beta leading to the fastest growth rate of the sequence an. So if you look at the previous page, what we got over here was we got, the special case when alpha and beta equals 1. That's not a case I'm allowing ourselves to consider. So maybe instead of saying that these equal 1, maybe we should do or 2 or 2 or 2, just so we can consider the previous case. Or even more generally, or some fixed number c. And this is how you do mathematics. You write something down, and you realize, maybe I didn't quite write down exactly what I should have. Let me tweak it a little bit. Let me try to find a good way. Let me try to generalize what I had before. For the Fibonacci numbers, each number is the sum of the previous two, and I'm weighting them equally. Well, what if I don't want to weight them equally? So one possibility, of course, is if they both sum to 1, that could be very different in terms of the behavior than if they both sum, if the weights sum to 2. Maybe if they both sum to 1, that might restrict as to whether or not anything can even grow, because I'm just averaging two quantities now. If I average two quantities, do you think I can get unbounded growth? So I need 2 people to volunteer. Give me a number. 3, give me a number. 7. Okay, I'm going to take an average of your numbers. Do you think my average could be greater than one of your numbers?
Yes.
Yes. Do you think it could be greater than both of your numbers?
Yes.
No. So if I take an average, it doesn't matter how I weight them. I could say, you're wearing a Williams College t-shirt. We've got to give you credit for that. So we're going to do 90% of the average will come from you. And
This is a local beer.
It's a local beer from New Zealand. Oh, see, if you had the beer on you, then that would be different. But this is like temptation now, and so we'll only consider 10% from yours. So we could definitely get our new number to be larger than yours and smaller than yours, but we're not going to get our average to be greater than the maximum. And so we know that the sequence can't get unbounded. And so if we force alpha and beta to equal 1, we might actually say, no, there's no way the sequence can grow. So it might be more reasonable to say, let's let the sum equal 2. And then we know in the special case, when we weigh equally, you grow at a rate of 1 plus root 5 over 2. You're growing geometrically, exponentially rapidly. What's the best? So anybody want to make a conjecture right now without doing any large calculations? Do you think the Fibonacci numbers is the fastest way to grow? Or do you think there's a better way? So let's do case 1, where we want the sum to equal 2. Fibonacci is treat everybody equally, very democratic. Do you think that's the fastest way to go? That gives you, what do you think might be better?
I think if you bias towards alpha, just because A is greater than A minus 1, then my intuition would say that would cause things to go faster than if we just wait that.
Okay, so it seems reasonable that the best growth rate, the fastest growth rate would be put everything in alpha. Because if the sequence is, non-decreasing, why the hell would I want to have anything to do with an minus 1? What if you wanted to go as slowly as possible? Put everything in beta. But now, what if I force not the sum to be 2, but maybe the sum of the squares or the sum of the square roots? Does that make a difference now? Or do you still say the argument doesn't really matter? I still want to put all of my eggs in one of those extreme baskets. Or is it better that if I move alpha down just a little bit, maybe because I'm taking a square root, I'm not losing as much now? And that it might be worth getting something in the beta, because maybe a little bit there becomes more powerful. What's the square root of 1 over 100? 1/10, so it comes up a lot. So maybe you shave off a little bit from alpha and put it in beta. That could be worthwhile. Whereas in the other one with the squares, maybe it's not worthwhile. So these are 3 problems to think about. I have not thought about them as to what's the best way to do them. But these would be great things to create a problem for the Fibonacci quarterly. And if people are interested, I think these are very accessible. And it starts to give you a feel for how things change. Okay. But hopefully this gives you the thought process of how do you take something that's standard and out there, and how do you create something new? And how do you correct when you make something that's stupid? If I force the sum to be 1, well, that's really not going to be that interesting in terms of a growth rate, because I'm taking averages. And if there's time today, that will actually be used by me as a segue into talking about averages. Okay, I want to talk a little bit about the tiling problem. I know people have looked at this a little bit. So the first one, we proved last time that if I do the standard 2 by n, it's the Fibonacci numbers for tiling, correct? So we did 2 by n tiled by 1 by 2 is the Fibonacci. And then the question is to do 2 by 2 by n by 1 by 1 by 2. What is that? Okay, and so I know some people have done some cases. So if we start off with the simple case, and hopefully this is not a horrible picture of the 2 by 2 by 1, how many ways? Okay, so the number of ways is 2. And it's basically, we can have 2 things vertically like this, or we can have 2 things horizontally like this. So does everyone agree that if it's 2 by 2 by 1, and we have 1 by 1 by 2 tiles, there's 2 ways to do it? All right. So What do we want to call our sequence? We need a name. C. Why C?
So I'm using C.
That's not a terrible name, but there is this thing called search and replace in the 21st century. When you see C, does that immediately make you think about this problem? I'm sorry? So you could do C for cubes, or maybe B for boxes, or T for tiling. We can do C. For today, we'll do C, but just think about naming, okay? So we will do C. So C1 is equal to 2. Probably the greatest example of ass kissing, I think, in the history of the world was, classically, we did not know of many planets. What were the planets going back to ancient times that people knew about? Now, this is a liberal arts college. You're supposed to be well-rounded. No, the planets. Which planets do people observe with the naked eye? Venus, Mercury. So let's do Mercury, Venus, Mars. You're skipping one. Mercury, Venus, Earth.
Yeah.
Right. Don't forget ourselves. Mars, Jupiter, Saturn. And that was it. Those were the only planets people could observe with the naked eye. And then Uranus was discovered. And the original proposed name was, by Herschel discovered, it was King George's star, named after his sovereign monarch, King George, who thought this was a wonderful idea. The rest of the world disagreed. And you can read about the compromise which led to being called Uranus, but as a, who should I name this planet after? How about my sovereign who controls my funding? Great name choice. Okay. Think about names. You want to be able to look down at a piece of paper and understand why. Why do you think they settled on Uranus? So you have to know a little bit about the ancient gods. Who was Jupiter's father?
Well, that's it.
Right. Want to guess who Jupiter's father might be based on the order of the planets and the naming? Nope.
Oh, Saturn.
Saturn.
is
Saturn.
Mars. Yeah, Saturn.
And then who do you think Saturn's father is? I believe that's why they went in that order, right? So there's often a reason why they do things the way they do. Try to think about it. There should be good reasons behind your naming. Make it as easy as possible for people to look down. One of the things that has bothered me enormously throughout the years is what function is 1 over cosine? What do we call that? Secant.
Oh, yeah.
And what do we call 1 over sine? Does that bother anyone else? There is a reason why they do this, and it has to do with what is the co of an angle. So there is reason, but when you look at it initially, it's like, this is just a nightmare for people to remember. Think about the naming. We'll call it C today because some of you have already started working on this problem, and to encourage you and be a supporting professor, we will go with C. But that's probably not the letter I would have chosen. All right. Now that we've got C1, let's try to figure out what C2 is. So now, we want to have something a little bit larger. And we want to figure out what is C2. And I believe several people got C2 equals 9. Okay. How did you get C2 equals 9?
I was walking home and I was trying to think about it in my head. As if it was a lot of like a Rubik's Cube.
Yes.
Sort of ways you can color pieces. Kind of starting with like, how are you with the tiling example for the kind of 2-dimensional case, and then start doing vertical pieces.
Good. So you're breaking it up into cases. And in fact, you even mentioned something that I love, Rubik's Cubes. In some years, I've actually made a requirement of this class that you have to be able to solve a 2x2 cube to pass. It takes about an hour to learn, and it's a good skill to have. It's not that bad to learn how to do a 2x2. I'm not saying to learn how to do a 2x2 well. I'm saying to learn how to do it 2 by 2. What's the minimum number of moves you need to learn to solve it? It's not that bad. So here, let's look at the possibilities. One possibility is we have 2 vertical like this, right? And now once we have that, how many possibilities do we have for the next? Then it's C1. So it's this times C1. And notice we're reducing it to a previous case. We could have 2 horizontal. And once we have 2 horizontal, what is it? C1. So now we've handled the case when we have 2 vertical. We've handled the case when we have 2 horizontal. So we now know we have to have at least one that is neither vertical nor horizontal, and it's going, inward. Is it possible to have only one going like that? No. Is it possible to have 2 going like that? Do they have to be next to each other, or could they be diagonal?
No.
They have to be next to each other because there's 2 options. They have to be, you could have all 4 of them going in.
Yeah.
You could have 2 going in. But if the 2 going in are diagonal from each other, then you're not going to be able to fill in the rest. Does everybody see that? So then the next possibilities is we could have all 4, going like this. If you will accept this as, some kind of picture for just one. Or we could have 2 together. How many exactly 2 together? So this is all 4 or just 2. How many ways could we have just 2? So I have to choose, I've got 4 spots. How many ways can I choose 2 of the 4 spots?
6.
There's 6, but that includes 2 things that are,
Oh, that's true, actually.
so it's 4, right? I could do the 2 top, top right, 2 bottom, bottom left, top left. So there's 4 ways to do this. And once we do 2 of them, say we do 2 top, then what would we have for the bottom? C1. So I think when we do all this together, we get C2 is C1 plus C1 plus 1 plus 4C1.
That doesn't
Yeah, because the first 2 C1s come from the 2 are vertical, 2 are horizontal. Then the 1 comes from the fact that I could have all 4 of them going the long way. And then the last one is I have 4 ways.
No, I think the last one is wrong.
Oh, the last one is wrong. Okay.
Just because with all 4, like you have the bottom example, the 2 going across and then C1.
Oh, yes.
It's 2 C1.
Right. So there's 4 ways to do this. But when we do the remainder, it's not C1.
It's just 1.
Why is it just 1?
Because we already have the.
Good. And that's the issue. So this is wrong. It's actually C1 minus 1. Because if we included, there's 2 possibilities for the bottom. Once we have all 4 going like this, I could have the 2 bottom going in the same direction or rotated 90. If they are all going in the same direction, that's the case I just counted before with all 4 of them going the same way. So now, this would then be not 4 times C1, but 4 times C1 minus 1. And I'm sorry?
So 6, 3, 6.
So this does, I think, come out to 9. And so this does equal 9. So is everybody comfortable that we got 9 at this point? All right, now I think we have 2 proposed recurrence relations for what comes next. So I was talking with one of my colleagues as to, is it easier to try to do this 3-dimensional problem Or would it be easier to try to look at how many ways could you tile a 3 by n, a 4 by n, a 5 by n in the plane and try to do that tiling problem? There's oftentimes more than one way you can generalize. I like the idea of just keeping the base of size, 2, and then just increasing the dimension. But you could, of course, go the other way. So anybody want to suggest how we try to do C3? Yes.
Consider the second plane on the third cube. So basically, you can consider T3 as like a combination of like two points, right?
Okay. So
if we consider like the plane that separates C2 and C1, we can basically partition all of the covers into like the case where there are no blocks that go between the plane that separates C1 and C2, and the ones that where there are pieces in the boundary. That was the way I came up with
okay, so it looks something like this.
so like call the green line, like say like B.
Okay, what do you want to call the green line?
B for boundary.
Okay.
Like small B.
Well, maybe let's call it B2. And then what could I call the red line? Right, so good, trying to think of good names. And the whole point is I want to come up with a recurrence relation that's going to somehow break this up. If I start off with 2 vertical or 2 horizontal, if I do something in just maybe we give different regions. So maybe this is the red over here. Maybe this is the green over here. And maybe I'll make this over here yellow. And call this B3 and call this yellow. So if I start off with 2 things in the red, I know what's going on. Right? Because then it's just going to give us C2. So we know C3. So how many ways can I put 2 things in just the red? And fill up the red? 2. And then once I fill that up, what's left over for the remainder? C2. So that does all the cases where I only put things in that first third, in the red part. Now we have to start looking about putting things that go between the first and the second. And there's a couple ways to do it. One way is we could do it in such a way that we completely fill the first 2 when we're done. But it's possible that maybe we have something where we don't completely fill the first 2. We maybe do 2 on the top, then 1 horizontally on the bottom, and then 2 more coming out. So the question is, what's the best way to go at this point? So we could divide it into 2 cases. We could say that for the next one, we're going to completely fill the first 2. And so one option, and plus dot dot dot. So one option is completely fill the first 2/3 and then move on. So how many ways can we fill the first 2/3? So that is C2, and then what do we multiply by for the last one? C1, right? Yes?
An issue I think with that is some of those combinations I think have been included.
Good. And so have we already included that with going forward? So with this double counts.
I think that like idea of
Wait, but we can fix this. So how would you fix it so you get rid of the double counts?
the segmenting, I think, not sure this which is like how we're keeping the pieces just in a read segment, let's say just have the like x to C1. And then the next kind of section of our equation will be pieces that go across.
Right. Right. But I'm saying if you wanted to do it this way, how would you fix the C2, C1 term to avoid the double counting?
C2 becomes 5 because we only count the cases where the break tile.
So we take away the cases where you have the first third covered by itself. And that would be C1 times C1.
Yeah. Well,
And that's going to give you 5. And then you would multiply that by C1. So here we remove the double counting. What I hope you're seeing is that this is getting to be a nightmare. And I've met with some of you outside of class to discuss some combinatorial problems like this, where it is so easy to accidentally double count something. And you want a good approach to avoid doing double counting like this. So what I want to do is I want to just introduce one other related recurrence problem, which I know some of you have sadly seen with me already. I apologize. And then for Friday's class, if somebody wants to present how you would come up with a good recurrence, that would be wonderful. But I want to just go through the dangers of stuff like this. So this is one of my favorite problems. I know at least one of you has seen these numbers in a research project with me. So this is what's called the Catalan numbers. So if you answer this question wrong, you can flunk the class. As a Bostonian, I hate New York City, but one part of New York City does something better than Boston. What will I accept as the answer?
I mean, the question is,
What part of, there's a part of New York City, I'll even give you which part, Manhattan, which does something better than the corresponding part in Boston. No, you do something like that, you're going to be in danger. It's going to be something as a mathematician.
Yeah.
What as a mathematician would I like about Manhattan?
Maybe the order of streets.
Good. So how are the streets done in Manhattan? In a grid. It's really easy to get around. In Boston, you actually have streets intersecting each other multiple times as to which one is on top. It can be a real nightmare to navigate. Manhattan has a wonderful grid system. So let's imagine we can only move on a grid and we can only move east, west, north, south. And so what I want to do is I want to start off at 0, 0. I want to end at NN, and I can only move east and north. So only move east and north. How many east steps do I need? How many north steps do I need? Need N of each. And the goal is I want to stay on or below the main diagonal. So first off, how many paths would there be from 0, 0 to NN only moving east and north?
in total?
In total.
I think it would be n plus n factorial over n factorial. Factorial?
Yes.
Yes.
And there's a nicer, simpler way to phrase that. 2 and choose N.
Yeah. So
Right?
That was not well phrased.
No, it was correct.
Yeah.
And you actually gave the logic. So the number, whoa. I'll do like this. The number of paths is 2n choose n. How many valid paths? Staying below the diagonal. So one possibility is a half of them. But the problem with that is you almost want to say, well, if I take a path that's below, I can reflect it and that's above. But
It's definitely less than half
because you could actually go back and forth. So you can have many paths where you go above and below and whatnot. So unfortunately, they normally use Cn to be the number of paths. And it can be shown that this is 1 over n plus 1, 2n choose n. It's at least reasonable. It's less than the total number of paths. Good. I shouldn't have more paths when I add a restriction. But it does seem to be saying that there's a large number of paths. And the reason I want to show you this is this introduces another really good concept in problem solving. Auxiliary quantities. When my kids were young, my students sometimes asked me, which kid do I love the most? And I know this is being recorded, so I'll be a little bit careful when I answer, but it was really easy to say which kid I loved the most when they were young. It's whoever did a better job sleeping the night before. I loved them both so much that was enough to give the tiebreak. How many of you have done multivariable calculus? Good, since this is a prerequisite for the course. Do you remember Lagrange multipliers to try to find constrained maximum and minimum? I have some function f. I want to find where is it maximized or minimized, subject to g of x, y, z has to also hold. And you introduce this auxiliary quantity lambda. And you have, I want the gradient of f equal lambda times the gradient of g, and g of x, y, z to be 0. At the end of the day, we don't care about lambda. It's just a quantity that's introduced to help us get to where we want to go. You might have seen this in geometry where you introduce auxiliary lines to try to prove something. We don't care about those lines. We care about the result at the end of the day. So we sometimes introduce auxiliary quantities which are easier to work with. And then we can kind of forget about them at the end of the day, but they help us with the calculation. So we're trying to do the Catalan numbers. So, we have something, like this, yada, yada. And I've got, some path like this. And Cn is the number of paths from 0, 0 to nn. I gotta use a capital N, I guess. Always on or below the main diagonal. And now I'm going to introduce an auxiliary quantity. Bn is going to be the number of paths from 0, 0 to nn such that you first hit the main diagonal at nn and below the rest of the time. So it's basically the first hit. So first hit the main diagonal at nn. If I look at valid paths from 0, 0 to nn, do I have to hit the main diagonal at least once? Good. So we know we have to hit the main diagonal at the end. So we know that if I look at any path from 0, 0 to nn that stays on or below the main diagonal, we know it hits the diagonal at least once. So we can segment based on where do you first hit. So what that means is we can write, Cn is how many times is the first hit going to be at 1, 1. So how would you figure out how many times is the first hit at 1, 1? Only once, but how would I use that in terms of what I've defined here? It's just what? What quantity represents I first hit the main diagonal at 1, 1? We don't have that many quantities on the board, right? We have Cn and we have Bn. Cn is how many paths do we have from 0, 0 to nn, where we're always on or below the main diagonal and we end at nn.
So Cn.
Bn is how many paths do we have from 0, 0 to NN, and NN is the first time we hit the main diagonal. So
maybe we could change CF, we could have like CF n plus 1, which is the number of paths from 1, 1 to NN that are always on or below the main diagonal.
there's definitely a relation, but it's just B1. If I want to know how many times do I first hit at 1, 1, it's just B1, right? So it's B1, so this is first hit at 1, 1. And now once I've hit at 1, 1, how many valid paths are there from 1, 1 to NN? At or below the main diagonal? Not BN, CN minus 1. Right? Once I've hit 1, 1, I now just have to have a valid path, and I just have to think that's 1 short. Or I could first hit at 2, 2. How many, what's the number of ways that I first hit at 2, 2? What would that be? B2. And now I have to complete. How many ways can I complete from there? CN minus 2. And I keep going all the way to I first hit at NN. And then that would just be BN times C0. And so we'll set C0 equal to 1. Which makes sense. This is the Seinfeld, there's one way to do nothing. I started 0, 0, I ended 0, 0. I want to say at or below the main diagonal, there's one way to do that. Do nothing. No steps east, no steps north. It's reasonable to define C0 to be 1. This is now a recurrence. The problem with this is twofold. One is the number of terms is growing with n, so this is a lot harder than the Fibonacci's. The second is involves both B's and C's. I've introduced an extra sequence, but I claim that there's a nice relation between the B's and the C's. So if you think about what's going on, I'm using black. So, here's everything again. Let's say I'm looking at BK. And so the first time I hit is at KK. If this is the first time I hit, where must I have been 1 moment earlier? Good. I had to be 1 unit lower. And we know my first step has to be a step to the east. Now, if you want, I can look at this region over here. And I claim that if I want to first hit at KK, the only way my first hit can be at KK is I had to, 1 moment earlier, I had to be at K minus 1K. And I know I have to start off at 0, 0, and then I have to move to 1, 0. So I'm really just counting how many paths are there from 1, 0 to K minus 1K, never going above that main diagonal. What is that number? How many paths do I have in here? Yeah, this is just C of K minus 1. So we get that BK is just going to equal CK minus 1. And this gives us our relationship, CN is going to be, it was B1, that becomes C0, and then it was CN minus 1, I believe. Yeah. So then that becomes C0, CN minus 1. So notice that the indices sum to n minus 1, plus, C1, CN minus 2, plus all the way down to the last one was Bn, which becomes Cn minus 1, C0. We now have a recurrence relation for the Catalan numbers only using the Catalan numbers. We introduced this auxiliary recurrence relation B, but we end up removing it at the end of the day. So I wanted to just get to here so that when you're trying to look at the tiling problem I gave you, it might be easier to break it up into some other recurrences as well. Because maybe you want to have some recurrences where some of those things are initially going in. And just really think about how easy it is to accidentally double count in the problem. All right, so on Friday, anybody who wants to present, I'll let you guys present on that. And then we'll go from this. If people want to do more inductions of recurrences, let me know. Otherwise, I want to move and start talking about inequalities, the mathematical kind. All right, so this is a good place to stop.